we're very fortunate to have Jeremiah Murphy, professor at Florida State University. He's an expert on core collapse supernovae. Coming to talk to us. He's been visiting since yesterday and will be here through tomorrow. So please sign up to listen. With that, please take it forward.
All right, thank you. And thank you for coming. Just to start off, if you have any questions throughout, feel free to interrupt me. I don't mind at all. So I'm going to be talking about how do massive stars die. I'm going to be introducing some theory, in particular conditions for explosions, and going towards actually making predictions. And then we'll also look at some constraints of which stars actually explode. So we're going to try to answer this question from both directions today. So the image in the background is of supernova 1987A, as it is seen today by the Hubble Space Telescope. The rings that you see in the inner part and then the outer part is not the explosion itself. The explosion itself, the ejecta of the explosion, is a little pink dot in the middle. It is resolved by HST, but those rings are not the explosion. So just to get us all on the same page, when you see, this is supernova 1987A in 87 when it blew up as seen from Earth. The amount of light in a typical supernova is 10 to the 49 ergs. The amount of kinetic energy that this explosion imparts into the interstellar medium is about 0.3 to 3 times 10 to the 51 ergs. So 100 times more than the amount that's coming out in light. And then as you will see later, neutrinos play a really important role in the explosions of these stars. Eventually, over about 10 seconds or so, a few times 10 to the 53 ergs come out in neutrinos, so a factor of 10,000 more than in light. In fact, if you calculate the luminosity of neutrinos, which is 10 to the 52 ergs per second, or a few, for about a second, it's as luminous as the entire visible sky of all the galaxies that you can see. So these are neutrino events. These were the handful of neutrinos that were detected with supernova 1987A. They basically confirm much of the story that I'm going to be telling you today. And from that, you can get some information about the mass and radius if you know the total amount of energy in neutrinos and the typical energy of each neutrino, so the temperature of the spectrum. You can learn something. These are predictions for what's going to happen for supernova in our galaxy. So Hyper-K will be able to get a few hundred to 1,000 neutrinos, and we will actually be able to see the neutrino signature as a function of time. And in fact, IceCube, the neutrinos from a supernova would actually correlate to a noise increase in IceCube, and so you would just see the noise level increase in IceCube. So you could actually use IceCube. But once again, these are for within the galaxy. There will be gravitational waves from a core collapse supernova. They are quite weak compared to what is capturing the news now. For example, they will only be detectable out to about 10 kiloparsecs, so well within our galaxy. So if Betelgeuse blows up, we will detect the neutrinos and we will detect the gravitational waves. It will be hard to observe it by telescopes, but at least we will detect those. If you have more questions about the gravitational waves, I can talk more about that later. I want to just continue on with my introduction. So if they successfully explode, they leave behind a neutron star, which this is the Crab pulsar. Or if they don't explode, they probably leave behind a stellar mass black hole. And this is important in creating neutron stars and black holes, but also all of the merger events that LIGO has been detecting recently, they ultimately start out as either a massive star that either exploded or didn't in a binary system. Nucleosynthesis is quite important for these. So this is the periodic table of elements. Coded in green is where most of the element comes from exploding massive stars. In orange, merging neutron stars. Not that long ago, it was thought that maybe this R process stuff here could be contributed both by massive stars and neutron stars. It tends to be favored towards merging of neutron stars today. But most of the elements that come out are produced by exploding massive stars. And in fact, oxygen, the amount of oxygen in the universe depends upon what fraction of stars above about 20 solar masses explode or not. And so that has been a constraint on that. All right, so let's go back to a little bit of theory. So here is your cartoon picture of a massive star as the iron core is about to collapse at the end of its life. Massive star is above 7.3 plus or minus 0.1 solar masses. You'll see why I put an uncertainty here. And down below about 60 to 100 solar masses. We don't know what the upper limit is for this mechanism. And at the center, you have this iron core. It builds up to 1.4 solar masses, and it has a radius of 3 kilometers, about the size of a planet. Now, I want to dispel a couple of misconceptions about core collapse supernovae. One is that the core collapses because burning iron is endothermic. So here is the binding energy as a function of mass number, and it's flipped, right? There's a minus sign here, so this is a minimum, actually. And so people usually talk about, okay, you get energy out by burning 2 iron, and then to get the rest of the stuff, you have to put in energy. And people often talk about that it is this endothermic process that causes a collapse. It is not. That is not the reason. The iron core is just an inert core. It's an inert core that has 10 to the 57 protons, neutrons, and electrons packed into 3,000 kilometers. And as a result, the dominant source of pressure is electron degeneracy pressure, just like a white dwarf. So the center of a massive star at the end of its life is essentially a white dwarf, but made of iron. And once you make this small, right, this is Heisenberg uncertainty principle, once you make this small, and that goes up because of the Heisenberg uncertainty principle, you have electron degeneracy pressure, but the electrons start to become relativistic, and when they become relativistic, it softens the equation of state, and that is what leads to collapse. Basically, it's the same thing as a Chandrasekhar mass object. That's why neutron stars are mostly 1.4 solar masses. All right, so now back to this picture. You have a Chandrasekhar mass object made mostly of iron, and it collapses on this time scale. That's less than a second. So 150 milliseconds, or 0.15 seconds, down to the size of a city. So all of those 10 to the 57 protons, neutrons, electrons get packed down into tens of kilometers. And then once it reaches this, then we have the second common misconception about core collapse, that the core halts its collapse due to neutron degeneracy pressure. That is not what's happening. What's happening is once you reach this size, all of these neutrons and protons are so close to one another that you essentially have a giant nucleus. It's an A of 10 to the 57. And once you do that, the neutrons or protons are so close to one another that the strong force takes over. And this is the effective potential of the residual strong force between two nucleons, in particular a proton and a neutron, in which you have, there's a very repulsive core, and then this is where the attraction would be, and that's where, so if you had a neutron sitting here, a proton would be sitting there. All right? And so it is this repulsive core that stops the collapse. And in fact, it is quite stiff. All right? And understanding this residual strong force and the many-body context is really important to understanding the consequences of core collapse supernovae. I'm not going to say much more about this story other than say it is important.
What happens when not?
If you, it just turns out that there's a little bit of degeneracy, but the effective force supplied by this is stronger. Yeah. Yeah, you would have to squeeze it even more for the neutron degeneracy pressure to go up enough to be competitive with this. But you're at the strong force. Okay. All right. So once you reach this size, all those neutrons and protons, the core stiffens, and just as high potential this hand, and it's going to fall, and then it hits my hand. When it stops, it sends out a sound wave, and that sound wave steepens into a blast wave. That's essentially what a blast wave is, a very strong sound wave. While the blast wave is traveling out, the rest of the star is trying to accrete at an accretion rate of 0.1 to 10 solar masses per second. All right? And so what happens is as this, there's a ram pressure of the rest of the star accreting through onto the neutron star, the shock's trying to go out, and behind the shock, the iron nuclei break apart into the free neutrons and protons. That takes a little bit of energy. There's also, you have electron capture onto neutrons, and onto protons, and you have positron capture on the neutrons, and you release neutrinos, and those take out energy. And so in the end, what it does is it saps the material behind the shock of energy, and the shock actually stalls into an accretion shock. All right? When the iron core collapsed to the size of the neutron star, much of that binding energy change went into heating up the neutron star into thermal energy. So the thermal energy is a few times 10 to the 53 ergs. And the challenge is how do you get this thermal energy out to a region just behind the shock so that it can help revive the explosion? Because if the thermal energy just stays there and it doesn't interact with this region, then you won't get an explosion, and you would get full core collapse to a black hole every single time. So that's the basic challenge. So this proto-neutron star cools diffusively by neutrinos. The time scale of cooling is about 10 seconds. The neutrino luminosity coming out from the neutron star is about 10 to the 52 ergs per second. And so with those two, you expect it to get 10 to the 51 ergs in here in about a second. So this is the neutrino transport that's happening everywhere. You have free protons and neutrons interior to the shock. You can capture neutrinos. Let's see which way to go. Okay, yeah, you can capture neutrinos, which neutrino absorption takes energy from the neutrino sector and puts it into the baryons. In other words, it heats the matter. Or you could go the other way, in which you emit a neutrino, which gives you cooling. These are the two predominant processes for neutrino interactions. There are many more, but I'm just showing the two dominant. And so this happens everywhere, both ways, but the details are a little important. So inside the neutron star, the diffusion length is about 10 meters. In here, the diffusion length is about 100 kilometers. And then out here, the diffusion length is it's basically free streaming because the diffusion length is infinite. And so you go from a diffusive regime to a free streaming regime, and in fact there is a neutrinosphere just like there is for the surface of the sun for a photosphere. It's right around 50 to 60 kilometers depending upon the energy of the neutrino that you consider. All right.
So we're saying neutrinosphere means the surface of loss scattering before.
Yep. Just like photons for the photosphere of the sun. All right, so the heating locally goes as the neutrino luminosity coming from the core times the cross-section divided by r squared. All right, the cooling everywhere goes like temperature to the 6th power, the cooling by neutrinos. This is the heating locally by neutrinos. The temperature, just because you're talking about something that's kind of in hydrostatic equilibrium, the temperature goes as 1 over r. So the cooling goes as 1 over r to the 6th. All right? So if you plot that, the heating versus cooling, the cooling curve is much steeper than the heating, and so what you end up is on the inside, cooling dominates heating, and the outside, heating dominates cooling. And so you have a heating region versus a cooling region. So the interior part, where the protoneutron star is cooling by neutrinos, and some of that does heat the layers exterior to that. All right, so there's a cooling region, and exterior to that is the gain region, which is heating. All right, and then the hope has been that if you can recapture about 10% of the neutrinos streaming through in this region here, then it's enough to relaunch the shock into explosion. All right, and so the fundamental question in core collapse supernova theory is how do you go from this stalled shock into a dynamic explosion? All right, and 1D simulations, if you do this in spherical symmetry, just have not worked, except for the least massive stars. We'll get to that soon. So stars around 7, 8, 9 solar masses, they explode even in spherical symmetry, but everything else does not. Okay? This is the shock radius versus time, right? Kilometers. So that's the shock radius. One is if you do gravity Newtonian, or if you do gravity in a relativistic way. Relativistic meaning GR included. All right. So here is an old simulation now, but it just gives you the characters. So there's the stalled shock. there's the neutron star. What you're looking at is entropy, so cool neutron star. This is the region that's being heated. Because it's being heated from below by neutrinos, just like setting a pot on a stove and it gets heated below, it boils, or there's convection. So there's neutrino-driven convection here. There's another instability that has to do with the shock that's called the standing accretion shock instability. I'm not going to talk too much about that here. In this particular simulation, I set the neutrino luminosity to understand how does this system respond to a certain neutrino luminosity, and so I forced this one to explode to see how it would explode. Okay? All right, so what you see is convection, and then later on, as it explodes, it's exploding aspherically. Now, more modern simulations, apparently David Vartanian was here last year giving a talk on this, show that basically if you do 1D, they don't explode. You do multi-D, they explode sometimes. Not always. All right, here's another group with another code. The code is Chimera. These are two-dimensional simulations. They're getting explosions for a 12, 15, 20, and 25 solar mass star, or progenitor. And this is showing the explosion energy as a function of time after bounce in milliseconds. There's a second. There's 1.4 seconds. And the energy is in betas, as in the person who won the Nobel Prize for the PP chain. 10 to the 51 ergs is also called a beta. All right, so the canonical explosion energy you're probably used to hearing is 10 to the 51 ergs. That's there. And what you want to look at is the solid curves, the explosion energies of the solid curves. All right? All of these do not go above 1. That's just what I want you to notice. One of them approaches 1, but it does not go above 1.
Doesn't 2D enhance your chances of explosion?
I would say no. So I can show you a plot which basically says that 2D and 3D are similar in terms of explodability, actually. You get similar outcomes. Now, whether or not explosion energy, that may be a different story, but we'll actually see that in a second. We'll compare 2D and 3D in that way as well. So,
what are we supposed to take away from that? That the asphericity that you need is sufficiently captured in 2D?
Yes, basically. I can explain that a little more when we talk about convection. Ask me that question again when we talk about convection. All right, so here is another code. Coconut FMT. It's done in 3 dimensions. Bernhard Müller did these simulations. Here are the explosion energies in 10 to the 50 ergs per time in seconds. And you notice there's a whole bunch of explosions, but the maximum explosion energy he found was 4 times 10 to the 50. Right? Here's another group with another code, Fornax in 2D and 3D. Basically, what you see is the explosion energies here are not that different in a second. All right, there they are. So thin is 2D, thick is 3D. All right, so there is a little bit of difference, but not huge. All right, so yeah, and you see that the explosion energy goes up to 10 to the minus 1 of beta in this case.
Sorry.
Yeah.
You said this and I missed it. The lines are terminating because
these simulations are really expensive.
Okay.
You'll see in a second.
Okay, so there's no, like, I'm just thinking how far they got at the...
Yeah. You know what? Actually, let me say something. Sometimes these simulations stop because of a bug, because of it encountered a problem, and it's and you just spent a lot of time getting there, and then you're like, crap, now I got to go back and figure out why it stopped. So sometimes they stop because they run out of time. Sometimes it stops because it enters a tricky regime. All right. So this is, I recently analyzed, I was noticing, the explosion energies seem to be less than what I thought were canonical explosion energies. So maybe we should look at that. As theorists, we're making predictions. So let's at least be quantitative and get a sense of where we're going. So these are all the explosion energy curves that I just showed you on one plot. And what I did is I just mathematically extrapolated what the explosion energy would be after infinite time. There's no physics in this extrapolations yet. This is just a mathematical extrapolation of these curves. All right, and then we're going to compare it to the explosion energies inferred from 40 type 2p supernovae. Then this is the explosion of a red supergiant. I'll get to that a little later. Now, when people infer explosion energies from the light curves of these supernovae, that's also an inference, right? And so you have to be careful. Both you're simulating and there's an inference here. But when you take all this and use their techniques for the observations and this technique for inferring what is the explosion energy giving a light curve, what you basically find here is that the mean is 8 times 10 to the 50 ergs, and then with a factor of 3 width. So it goes from 0.3 to 3 times 10 to the 51 in terms of energies. And then what I did is I just compared this distribution with the distribution of energies from simulations so far in a Bayesian way to figure out what is the difference between the simulations and the observations. And that's this plot. So this is since I was doing a Bayesian inference, this is probably a distribution function for what is the likely difference between the observations and simulations for each set of codes. All right, and this is observation divided by simulation. All right, and so if this were 1, this would be 0 over here. This group, their simulation energies are under-energetic compared to observation by a factor of 3. This group under-energetic by a factor of 10. All right, now, I don't know which one is right. All we're saying right now is there's a quantitative difference between simulations and observations. As a community, we need to understand this, both on the simulation side and on the observational side. Yeah?
So the width is a factor of 3, and then there's a factor of 3 difference, so it doesn't seem to be that bad.
Well, so this distribution is formally not consistent with 0. However, the distribution between simulations, it could be consistent with 0. So yeah, right now there's a slight tension, but it's, yes, so that's right. Right now there's a slight tension. But this is a systematic offset between codes. Yeah?
I would say, I don't know, I'm not even sure that there is a tension here, given that the explosion energies as perceived from these simulations, which are only running for like of order a second, if even that. And given that the protoneutron star is cooling for 10 to 20 seconds and outputting kind of significant energy in that time, I don't know.
But isn't that the point of the analytic continuation here?
Yeah.
But like, so I feel like so.
Yeah. So like
there are
these.
a number of ways that you could extrapolate.
Yeah, you're wondering if this is going to start turning up due to another mechanism. That's possible. The protoneutron star wind is quite weak, and so I'm a little skeptical that it's going to add a lot more energy to basically resolve this problem. It's something that someone could look at, which no one has done yet. Partly because no one's no one's quantified this yet until now. So we need to quantify this. So.
The different codes are getting different values. Are they using similar neutrino physics, dimensionality, and initial conditions for the...
What you see here is a range of 2D and 3D. But the physics is they're all approximations to a neutrino transport of some sort. And they all decide to do their own approximation to neutrino transport. And that is probably the main difference. It's actually hard to tell what is the main difference, but that's probably the main difference. Right, these codes are complex with a lot of moving parts, and when you poke it in one side, it tends to move over here, and so it's just really hard to really pin down these things.
Because you have terms that you can't even compare, right? Because the small changes will end up with different realizations.
Well, yeah, I mean, yeah, sure. Okay. So the primary result of the last 3 decades is simulations rarely explode, yet multi-D simulations often do, but not always. So why? And which progenitors explode? All right. So T. Suchbold has investigated kind of the core structure of these stars to investigate how likely are they to explode. This is iron core mass as a function of the 0H main sequence mass. These are probably easy to explode. These are probably hard to explode. but that correspondence between core mass and explosion is not 1-to-1. I'll show you why in a second. So this one group, and note down at these low masses, there's a large variation for at a given mass, plus or minus 0.01 solar masses. You can get a large variation in what the core mass might be. So there's some stochastic nature to the cores of these massive stars. And so if you're going to try to make predictions, you're going to have to run these simulations on thousands of progenitors to see what's going to happen.
What's the main dispersion caused by mass loss?
No, this is due to so the evolution of the interior part of a massive star is pretty complicated in that it has core burning and shell burning at multiple levels, and depending upon so they use one prescription. Oh, sorry, were you asking what's the difference between this? Okay, what's caused the scatter? Yeah, it's basically an interaction between the different. So once you have one type of core burning, like carbon core burning, for example, or carbon shell burning, it leaves an entropy imprint in the star. And then when the next phase of like whatever silicon burning starts on, it imprints itself on top of that. And there's a complicated series of shell burning that apparently leads to this kind of stochastic structure in the core. Yeah.
Sorry, are these progenitors 1D?
Yeah, these progenitors are 1D. Yeah. Yep. Okay, so numerical simulations are important, but they cost 18 million CPU hours per run. They take months on 16,000 cores. That's $1 million per run. Or it'll power 1,000 homes for a year. All right? So to systematically explore progenitors in the physics would take hundreds of years with this approach. We need something else. We clearly do. All right, so we need another approach. One approach is to force 1D simulations to explode that match either the observed supernovae or simulations, or hopefully both. So remember this plot by T. Sipwold? Well, he took these progenitors. It was actually an earlier paper, but similar types of progenitors. And he collaborated with a group in MPA to force explosions in 1D. And they calibrated these explosions to show the properties of supernova in 1987A. And what they found is that depending upon your prescription for this forcing, you basically get, sometimes you get explosion, which is the green, or black holes. And the blue is exploding, but then fall back, forms a black hole. So most of the time, you either get explosion of a neutron star or black hole. And then there are these islands of explodability, like here, and then islands of black hole formation.
Sometimes both, it looks like. Every now and then you get a blue, which is, it explodes, but it makes a black hole.
Yeah, that's right. Yeah. Okay. Yet explosions that I just showed you are inherently multidimensional. So do these explosions represent nature or even the simulations? So while this is a prediction, which we should check, it's not clear that it's a prediction that would bear out once we actually are able to do this with simulations. Okay, so back to this equation. So let's try to understand the physics of explosion a little bit. All right, so let's go back to this cartoon model where there's the neutron star, it's cooling by neutrinos here, and it's heating by neutrinos there. There's the shock, and mass is accreting in. This thing sits around for quite a while, and so you can basically approximate the time-dependent terms to be 0. And you can find you can define a boundary value problem which gives you the structure in between the neutron star and the shock for this material here. And the structure depends upon kind of 5 parameters. The neutrino luminosity coming from the neutron star, the temperature of the neutrinos, or the spectrum coming from the neutron star, the size of the neutron star, the mass of the neutron star, and the accretion rate holding down the shock. All right? And so you can look for solutions in which you have a stalled accretion shock in this way. And so back in '93, Adam Burrows and John Gashi did this, and what they found was below a certain neutrino luminosity and m dot curve, they found steady state accretion solutions, and above they were not able to find solutions. And they proposed that maybe this is a critical curve for explosion. Note that they did not show that you get explosions up here, but just that you don't get steady state accretion solutions. So this has been a pretty useful metric. About a decade ago, I investigated whether or not this situation realizes itself within the simulations. So this is that original curve. here's the neutrino luminosity in 10 to the 52 ergs per second, here's the accretion rate. And I ran 1D simulations, and I noted the neutrino luminosity when it exploded, and the m dot when it exploded, and those points fall on this curve. If you do this in 2 dimensions, you find a curve that is 30% lower. And so this was a good way for us to quantify how much easier it is to explode in multi-D compared to 1D. Apparently, it requires 30% less neutrino luminosity to explode in multi-D compared to 1D. And since then, people have done this again and again in 2D and 3D, and that's what I was talking about in the comparison between 2D and 3D. Basically, the 3D points lie on top of the 2D points. There is some offset, but is it systematic one way or another? Sometimes it is, sometimes it's jittery. It's not clear to me. There's probably like a difference of 5% on the order of when this is 30%. Okay, so a question is, can one derive this reduction due to convection, and what causes this reduction due to convection? So first of all, there's a clean curve here, and as a theorist, anytime I see a curve like that, maybe I can explain that analytically. I've done that. I'm not going to go over that for this curve. What I'm going to talk about is the reduction, because that's interesting. So here are the continuity equations for mass, momentum, and energy that you would solve in one of these simulations, or if you set the time-dependent part to 0 and solve for the steady state. All right, so those are the equations. The important thing is we're going to Reynolds decompose these equations into the background part and the perturbed part, wherever you see a prime as a perturbed part. And this mass equation, well, let me go down to, this is the time-independent representation of the momentum equation, and what you end up with is a divergence of the Reynolds stress. All right, and when you do that for the energy equation, you end up with a turbulent flux, so this is the convective flux, and then turbulent dissipation. So you end up with these 3 extra variables, but you haven't introduced 3 extra equations. So there's a closure problem. And so you have to develop some sort of model to close this so that you can find solutions for this given the background solution. And that's quite difficult. It's something that I worked on starting in 2013. We developed a model, and then because we can control which terms go in here, we can see which of these terms are actually important in reducing this critical curve if we're able to get the reduction in critical curve.
So the 2 terms on the left, the 2 measurables, they don't change the net energy of the net momentum.
This one?
No, so
and then this one?
The red circles, the 2 in the red circles, they don't change the net energy momentum, but the one on the right does. So the row not, it's okay. It's okay. So
yes, this, yeah.
This does change the net energy.
This changes the net energy. This pushes flux around.
Right.
Yeah.
So because there's a gradient in front, so it doesn't change the net, the total integrated energy. But
oh, it does not change the total integrated if you were to integrate this over the total volume.
But the last one over there does. So where does this energy?
This one?
No, go on to
This one?
Yes.
That's turbulent dissipation.
Yeah, but where does this energy come from? From what?
It comes from the buoyant driving. Yeah, so if you Reynolds decompose this equation, you end up with a rho prime v prime times g term, and that's buoyant driving. And the assumption here is that that term is balanced by turbulent dissipation. Yeah. Okay, so we're going to investigate which terms are important. So Quinta Mabanta, who is a graduate student working with me, is about to graduate actually, did this investigation. This is the original critical curve. And then by doing this, by including this convection model, we were able to reduce the critical curve by about 30%, which is consistent with what we saw in the simulations. Furthermore, when we investigate which of the terms are important, this dotted line is only including the Reynolds stress term in the momentum equation, and so it brings down the critical curve down to here. But if you include the turbulent dissipation term only, then it brings the critical curve down here. So both are important, but the turbulent dissipation turned out to be more important. Okay, so now that we understand how convection aids explosion, it's through this turbulent dissipation and a little bit of the ram pressure, let's include it in a time-dependent, one-dimensional model, which we call 1D plus, so, and then see if we can reproduce the explosion conditions we see in multi-dimensional simulations and get those in 1D. So once again, it's the similar equations, except now there's time-dependent terms over here. So we're running this in a...
So you have a way of cooking up this...
Yeah, this prescription. It's like an alpha prescription model, but this is a global convection model. I borrowed from the atmospheric sciences community, which have gone way past alpha models for a long time. So I borrowed some of what they were using to develop this convection model and just put it in a one-dimensional radiation hydrodynamics code.
There are three parameters you tune it to make 30% reduction?
So yes and no. So it turns out there is a parameter that's basically what fraction of the neutrino power goes into turbulent dissipation versus turbulent flux. And I calibrated that using three-dimensional simulations and two-dimensional simulations. They're not that different, but we changed that parameter, and it actually doesn't change the results of this that much, actually. So, yeah. Oh, yeah, yeah, great. So that's here. So in a, if you, right, you're probably aware that in 2D, there's this energy cascade up to large scales and 3D energy cascade down to small scales, right? And so there's some differences that you might see there. And when you look at the simulations, like 2D has these big, large lobes, and then 3D is more small scales. But this dissipation is of order V cubed over L. And what's driving this? Well, what's driving this is the buoyancy in the presence of gravity. Gravity is the same in both cases. So it turns out this is mostly the same. There is a little difference, and that's where we were talking about this parameter a second ago. And so in some ways it's different, but what matters globally, it turns out it's not that different. And that's why I think the critical condition is not that different between the two, empirically in simulations. All right, so let's include this model in 1D simulations. So this is the result. So 1D radiation hydrodynamic simulation in collaboration with Josh Dolans and Fornax, his code. And this would be the critical curve that you get. Here is 2D, right? So 1D versus 2D. So there's that reduction of 30%. And here we add this prescription as the 1D plus, as the red and black stars. And they pretty much give the same results. And here's that alpha, which determines what fraction of it goes into turbulent dissipation. One of these numbers is for 2D and one is for 3D. I don't remember off the top of my head because it did make a difference to us and I didn't need to remember it. But I can find out which one is which. All right, so this 1D plus code is 100 times faster than 2D. And it could be up to 10 to the 5 times faster than 3D. All right, so you see where we're going to go soon. We haven't done that yet. All right. So that's a little bit of progress on theory. Now I'm going to start introducing a little more theory in terms of these explosion energies. So remember these explosion energy curves. Notice that they're monotonic and they're relatively smooth. Once again, can I explain this analytically? So Mariam, who's a graduate student working with me, has been working on this, and we're about to publish this paper. The model is basically, let's look at the evolution of this material here, which is being heated, because that's basically the material that gets launched during explosion. But let's treat it in a very simplistic way. So a one-zone model that is evolves as a spherical shell. So very simple. And the point here is we want to derive the important dimensionless parameters of this problem, the explosion. And we want to derive how energy depends upon these parameters. We want the important scalings. All right? And then we want to see what it would take to adjust the explosion energies of simulations once we have these scalings. All right? So let me see what time it is. Yeah, okay. Have some time. So step one, if a theory is to be universal, then we should write down a dimensionless equation, right? So dimensions are arbitrary, however scales are not. So I'm going to introduce you the scales in this theory. So we're going to scale the radius by the initial shock radius, or where this starts. We're going to scale all velocities by the dynamical speed, or the free fall speed at the shock. And then we're going to scale the time by the dynamical time at the shock. So it's just the free fall time divided by the size of the shock. And then the pressure we're going to scale by, this starts out in near hydrostatic equilibrium, so it's scaled by that initial pressure. These are the equations that you end up with, the dimensionless equations. And what you note here is that there is no dependence on the specific problem except for this one parameter here, eta. So this is gravity, for example, that's gradients of pressure. This is adiabatic cooling, and this is heating by neutrinos in that layer. And you notice that the heating goes down as 1 over r to the 5th. And so this heating time scale is basically the ratio of the dynamical time scale divided by the heating time scale. And the solution to those equations give you this dimensionless energy as a function of the dimensionless time, parameterized by the value of eta. And note there's an initial phase in which the neutrinos are launching the explosion, and then it just gets far enough away because of 1 over r to the 5th that it just coasts in terms of energy. We note that there is an asymptotic behavior here, and it turns out that the energy after infinite time goes as eta to the 2/3. The dimensionful explosion energy, which is what we need, is this dimensionless times some characteristic energy, which would be mass in this gain region, times the characteristic velocity squared that we started with. All right, and so if we plug this into there, this is what the dimensionful explosion energy is after infinite time for this model. It goes as the neutrino.
The explosion was going to be successful. Like,
What's that?
wasn't there something here that this explosion
Yeah.
was successful?
Yes, that's right. There is some.
Baked into the model?
Yes, I actually start the model in a situation that it's on the verge. It's reached the critical condition. I start it there, and then we ask, what is the evolution past there? Yeah. All right. So these, the thin dark line is the results from the simulation, and this gray band is our fit using this model. And we get good fits for low masses, which are mostly spherical explosions. So if there was any hope that this model was going to fit anything, it was going to be these guys. And it fits them quite well, in fact. So we're able to explain the explosion energies. So now, note, by the way, if you want this thing to be a factor of 3 more energetic in explosion energy, now we know what we need to do to the neutrino luminosity or the opacity or the size of the shock or the mass of the gain region to get there. And that's hard to do, especially when the neutrino luminosity is within the 2/3 power. We also, this once again is our model trying to fit to simulations. And note we get horrible fits, and these are poor fits that are mostly aspherical explosions. So there's no surprise there that we were not able to fit the mostly aspherical explosions, which tend to be the high mass progenitors. Some low mass progenitors, you can see this one doesn't do a good job of fitting either. All right, so this result is consistent with the hypothesis that the explosion sometimes is in part driven by aspherical dynamics, and in fact probably for most of the mass range that explodes. Okay, so that's very fast run through of some theory. Now let me go to some observational constraints. All right, so supernovae, as observed, you look at the spectrum to see if there's hydrogen. If there is, type 2. If not, type 1. Further classify the type 2s based upon light curve and sometimes spectrum. So if there's a plateau phase, it's type 2p. If it's a linear phase, it's type 2l. Then we ask, okay, are there silicon features? If yes, then it was a 1a, so it's a thermonuclear explosion. If no, then we ask, are there helium features? Oh my gosh, this is tedious. And then, yes, we have 1Bs and 1Cs. What I'm getting to is that all of these are core collapse in origin in the theory, and these are the observational consequences of those. These are the expected progenitors for each type of supernova. So the type 2Ps, which have a lot of hydrogen around, the progenitors are expected to be red supergiants, and in the wild, red supergiants are observed to have masses from 8 to 30 solar masses. And these are expected to be blue supergiants, which, who knows what's going on there in terms of mass, maybe binarity, who knows? And then the type 1Bs and 1Cs, which are the hydrogen has all been stripped, and sometimes even the helium has been stripped, that would be over here. You have two competing theories of what's producing these. Either stars with masses greater than 30 solar masses or binarity. My bet is both. But it's probably binarity that's dominating that. I don't have time to go into that story. So how do we determine what is the progenitor of these explosions? Historically, what you do is there's a supernova, and you hope HST accidentally observed that region before the explosion. So you get an image. You are able to resolve the star. In this case, it was a type 2P, so that would be a red supergiant. And then you get, with HST photometry, you construct a crude SED, where here's magnitude versus wavelength. And here's a spectrum. And then what you do is you say, OK, I have a spectrum here. I need to add a big bolometric correction to this to get the bolometric luminosity. And from there, you infer a mass. All right. Using this technique, there are now about 30 detections and 38 upper limits in progenitors associated with supernovae. Stephen Smart put together this nice little summary of log luminosity versus effective temperature. Here are the stellar evolution tracks. And these black dots are the observations of these red supergiant progenitors for observed supernovae, and these are the upper limits. All right? And basically what you note is, like, even this brightest one here, the track that fits it is about a 16 solar mass star. So Stephen Smart asked, well, let me infer a minimum mass and a maximum mass, and then I'll fix the slope in between of the progenitor distribution for these things that explode to saltpeter. But let me just infer a minimum mass and maximum mass. He found a minimum mass of 9, basically plus or minus 1, and a maximum mass for red supergiants going into type 2Ps, this is not all supernovae, the particular class, of about 16 solar masses, which is lower than the 30 solar masses. So they coined this the red supergiant problem. However, more recently, Ben Davies asked the question, okay, you're dealing with small number statistics. The distribution is pretty steep, so you're not going to have a lot of the really bright ones anyway. And so he asked the question, what is the probability of observing a maximum red supergiant luminosity, given that you only draw 10 red supergiant progenitors from this distribution, and there's the curve. Within 95% confidence, you could, that brightest red supergiant that you draw from this population could be down here, right? When the observed maximum luminosity is up there. That would correspond to 30 solar masses. And then he plotted the brightest red supergiant associated with the supernova as a function of as this sample size increased. And he noticed that the brightest red supergiant was going up and following the edge of this error distribution. And so to him, what he concludes is this result that you get 16 solar masses from these is not, and also being the maximum red supergiant exploding as a type 2P is probably not statistically significant. You have to wait until you get over here, but the problem is that this direct detection technique gives you about 2 progenitors per year. And so we would have 100 progenitors in 2050 to resolve this problem. What's that? Yeah, that's a good question.
Sorry, does W first solve this problem?
Huh?
W first.
Will it help?
Yeah, right, because when they go up, you have essentially the same imaging resolution, multi-band photography, and
A wider field of view.
much wider field of view.
Yeah, it'll probably help.
So the serendipitous likelihood of
Yeah,
something.
it'll probably help. Yeah, it might help.
I mean, the field of view is 100 times bigger, right? So your rate.
Yeah, but yeah, I mean, it might help. The thing is that you need to do this out to 20 megaparsecs, which the size of a galaxy is the size of your field of view. For HST, yeah, I mean, it might help. Yeah, we'll see. Maybe that rate would go up.
So if you limit it to 20 megaparsecs, so if you wanted to design a strategy, wouldn't you prefer to focus at the Berkeley cluster, for example. But if you're only interested in close-in galaxies.
Yeah, I mean, so there are techniques to look for. The problem is, yeah, I mean, you really need to be well within 20 megaparsecs, and you want a volume-limited sample so that you're complete. Yeah. All right, so we need another technique to verify the theory and to get hundreds of progenitors. All right, so the age of a star is given by the fuel in rest mass c squared divided by the luminosity. You've all done this. The luminosity goes to m to the 3.5. So that means the age goes as 1 over mass to the 2.5. So if you can... once you, it's no longer true once you get up to like 30 solar masses and above. You're right. There's a trend that's like this. Luminosity as a function of mass, you can get an age as a function of mass. Yes. And so there's a connection between age and the brightest star that's around. Right? So just to give a sense of things, 1 solar mass, 10 billion years. A 7.5 solar mass star is 45 million years. A 15 solar mass is 15 million years. And then a 50 solar mass is around 5 million years. All right, so the technique that we're employing that allows us to get many more, hundreds of progenitors, is we're age dating the stars surrounding either supernovae or supernova remnants. So there was an event that went off here. You use HST, you identify all the stars that are there, and then you age date those stars, and then infer a mass. So that's the technique that we're using. And note, you don't have to see the progenitor to do this technique. You can do this after it exploded, or even for a supernova remnant, which you didn't even see the explosion, but you know it was there, and you know these stars are associated with it. All right. So I'm just going to say, there are many more supernova remnants per galaxy than supernovae. There's 200 per galaxy. And so we've looked at relatively nearby galaxies, and we have a sample of about 300 supernova remnants with progenitor masses. All right, and what I'm going to do is I'm just going to quickly go by this, and then you can ask me questions later. I just want to get to some of the things here. So what you do is you make a color magnitude diagram in which you plot down the magnitude and the color of each star, and then you develop a model, which is the gray in the background, to try to reproduce that color magnitude diagram. This is the star formation history as a function of age. It's cumulative. And for this particular system, there was a burst of star formation around 38 million years, which corresponds to a mass of a little more than 8 solar masses. So, but sometimes we get this, and the reason you get this is because you can have multiple bursts of star formation in one place recently. And we don't know which of these is associated with the supernova or supernova remnant, but one of them is. So statistically, we can make an inference. And let me get to the main result. We've done this for M31 and M33. Let me get past this. We're going to once again fit for the minimum age, which is 4 million years, but that's our detection limit. The maximum age is 50 plus or minus 1 million years, and then there's a slope in this age distribution. Now let me translate that age distribution into a mass distribution. That will be a minimum mass of 7.3 plus or minus 0.1, a maximum mass greater than 60 solar masses, basically because our technique saturates at about 5 million years. And then a slope that is slightly steeper than saltpeter. It's minus 2.96. So this is consistent with theory, but we have pretty tight constraints. Notice these are statistical constraints and not systematic. Yeah. And maybe there's another parameter that sets black hole formation. And this is steeper than saltpeter. It either means that the most massive stars are exploding less frequently, or there's a significant bias in using supernova remnants. And with that, I'll just say that we're going to do the Bayesian inference for the 200 more in M33 soon, which is, there's the distribution. So we see a minimum mass around 8 solar masses. All right, and with that, I'll leave these main results up, and thank you for your attention.
Okay, go ahead.
So for your method, does it matter if it's a filled star or if it's in a cluster? Or do you treat it differently?
The assumption is that stars are born together. To make this work, the assumption is that stars are born together.
Right.
Yeah. That if you're basically age dating the siblings of the thing that exploded.
Okay, any other questions? If not, let's thank Jeremiah again.